Hello, welcome to this first video of CENG43 Strength of Materials. In this video, we'll learn how statics, which is the course that you should have taken before Strength of Materials, relates to understanding the behavior of materials. We'll also learn about what does a stress mean, which is the foundational concept that we'll cover in Strength of Materials. And also we will learn about the different types of stresses. So in statics, what we learned is how to analyze the structures and the equilibrium of structures and forces that are acting on them. So we have the loads acting on the structure, and the goal is to calculate the reactions applied or resulting in the supports, and also we were able to calculate the internal forces within the members. So like we see here, the main tool we used is free body diagram, and then we applied equilibrium equations for analyzing the equilibrium of these forces. So we have here two pins at A and C, and then we have the load. This is a very basic free body diagram. It doesn't use knowledge that we had, which is two force members. So a two force member, AB and CB. These two force members, I can recognize them because there is no load along their length and they are pinned at both ends. But here I'm trying to use the very basic free body diagram to model the structure. So once you put the reactions in the free body diagram, you can actually now start analyzing parts of it. So we learned that if we imagine that this is a frame, so we can dismember part of it, so member AB, and we can analyze its own equilibrium equations. And when you dismember it, the equilibrium or this dismembering reveals the internal forces at B. So we have here, these did not show in the overall free body diagram, but now they are showing up because we have that specific member analyzed by itself. If we think of this structure now as a truss, because it is, if you think about it, these are two force members. Now we can use the method of joints to analyze B and analyze the equilibrium there. So we're not really covering statics and details here, but at the end we use the knowledge from statics to calculate the action forces and internal forces. Now we move to another phase, which is trying to answer this new question here. So the question is, will each one of these members be able to carry or withstand the internal forces acting on them? So as a two force members, we only have like compression and tension. But the question is this cross section here with a diameter of 20 millimeters is enough? This bar with a depth of 50 millimeters, is it enough to carry on or carry the compression force within member AB? So we need to answer this question, we need to learn about stresses or internal stresses within each one of these members. It's not the stress we have from work, it's actually stress here as a force per unit area. So this is a member that I kind of cut and revealed the internal force within. Now the idea is we calculate the internal stress of this internal force on that cross-sectional area A. So we call, for this case here, it's an axial force that results in a normal stress, sigma, which is equal to force over the area. And the idea here is we normalize the impact of this internal force by dividing it over the area. So I have a unit force per unit area, or a force per unit area, and that will help us to really kind of translate that basic understanding of this problem here. So I have here a 2 feet diameter kind of structure or a member, and then a 2-inch diameter member subject to the same force. So logically, you don't need strength of materials to answer that, but of course you feel that this member here is under a lot of stress because it's slim. So how we got that is by stresses. We normalize the impact of this same force by dividing it over the area, and now we can see that the stress on this member is more than the stress on the bigger one. So with stresses, we can now do design of members. So we can pick an appropriate material for this member, steel versus wood versus aluminum, and also a sufficient cross-section size. So we can meet up this, beef it up to the point that's just enough for withstanding or carrying on the resulting stress. So it has very economical consequences here. We don't want to put a lot of materials in a cross section, and we don't want to pick a material that's too strong for this application. So over the course, we'll see three main types of stresses. Two are very critical and main, and the third one is a stress that happens in special cases. So normal stress, like we see in these two force members, AB and BC, they are under compression and tension. So we have here a direct generation of normal stresses. Normal stresses can be generated from other cases of loading, which we'll see in next lesson. Shear stress happens when you have that shearing action. So the bolts or the pins of these two supports have these shearing actions between that member that wants to kick out or push in the wall and the pin that's holding it. So that pin is under shear. And then the bearing stress, which happens here between the contact area of the bolt or the pin and the member that's connected to it. So there's this contact surface area, there is a pressure in between, so there's a crushing that tends to happen there, and we're trying to analyze also the stresses applied there. So that was a very brief introduction to stresses and the overall course of strength of materials. Looking forward to learning more about these type of stresses with you in the next videos. Thank you so much.